Welcome to my first installment of video here on AP Chemistry for Mr. Freidus' class. Our first lesson is going to be on molecular geometry. So you can see here we gave you some shapes. We learned about these shapes last year. We're talking about what these molecules physically look like. All right, so obviously linear is a straight line all the way down maybe to trigonal pyramidal, which looks like a pyramid with 3 legs to it. All right, so we'll talk about all of these different shapes. All righty. As we've talked about, the shapes affect reactivity. So whether something's polar or non-polar depends on if it's symmetric or asymmetric. So these shapes have an effect on all of this. Okay, we're going to be talking a lot about bonding and non-bonding electron pairs. Okay, everything they're showing here are bonded electron pairs or bonding electron pairs. Okay, so basically the lines in between a central atom and some outside or satellite atoms, those are bonding pairs. The non-bonding pairs of electrons would look like the little dots. Okay, I might put them right there. Okay, it might look like that. All right, these would be the non-bonding pairs. Oops, trying to get my laser pointer here. All right, so electron pairs repel each other. So this is the key concept here. If we look at these electrons, they are going to be repelling the pair of electrons next to them, whether they're bonding or not. So these want to push these away. So if we were to look, this will have a force of repulsion pushing these other electrons farther away. Okay. Likewise, these electrons push the other electrons away as well. All right, so you've got combating electrons pushing each other, and the result is your shape tries to find the best symmetry or the optimal angles. Okay, in this case, when we've got 4 pairs, all right, so if we look at it, we've got 1, 2, 3, 4 pairs. Okay, the optimal angle is going to be 90 degrees. So roughly 90 degrees between these angles here. All right, so they form as far apart as possible from each other. I'm talking about. So we're really talking about electron domain geometry right now. We're going to talk about 2 geometries. The first is electron domain. That includes the non-bonded pairs. So these electrons that are not bonded on the central atoms. We're not worried about these non-bonded pairs on the satellite atoms, really only the pairs on the central atoms. And when we're talking about electron domain geometry, we take those into account. The other one we're going to talk about is the actual molecular geometry, which is the visible shape, which doesn't include those non-bonded pairs. All right, so here's your vocabulary. The bonded pairs, okay, are the ones that attach to from a central atom to a satellite atom, and then your non-bonded pairs are just as we talked, okay, these 2 here that are not attached to a second atom. All right, so single, double, or triple bonds count as only 1 electron domain. So in this case, let's look at this other atom down here. We will have 1, 2, and 3 pairs, bonded pairs, but then we also include this one here. Okay, down here, that's going to be number 4. Let's see if I can draw a 4 with this. Not bad, not great. So those are our 4 electron domains right there. Some more quick vocabulary. Central atom, okay, we're going to use, in our terminology, we'll call that atom A. They're calling these atoms bonded to this. I call these satellite atoms, okay, atoms B. They are the ones attached to the central atom. All right, and then we talk about the non-bonding electron pairs. Okay, so we're only talking about any item that's surrounding the central atom. All right, so anything around here. Okay, so 1, 2, 3, 4 different things. So VSEPR, valence shell electron pair repulsion theory, is basically what we stated. These electron pairs want to push each other away. So here we have a tetrahedral shape. We've talked about those in the past. If all of these are the same atom, which there's theoretically all chlorine here, all right, these electron pairs will have equal repulsion. So they will find the optimum angle in a three-dimensional space so that they have the maximum angle from each other, and that angle will be the same. So we have 109.5 between these two. Electron pair repulsion theory states we'll also have 109.5 there, 109.5 there, and 109.5 there. So, and actually, if you wanted to go around the back, 109.5 there. Okay. You could even do this one. Now it's getting really confusing. All right, all of the angles involved will be 109.5 because they've got equal repulsion from each other. Okay, so this ensures the best arrangement of a given number of electron domains is the one that minimizes the repulsions. Okay, so the farther apart they push each other, the less repelling force they will have. All right, so here's our general, again, we're talking electron domain geometry. So this is including the non-bonding electron pairs, okay? So this is not what we visibly see. This is where we have a pair. This includes anything coming off the central atom. So we have linear. I'll tell you what, I'm gonna go ahead and show all the next stuff so we can talk about it all at the same time. So here's linear, okay? Its general form is AB2. Remember, A is the central atom, B is the satellite atoms, and it's going to look something like this. The maximum angle, if it's linear, hopefully you guys are good at geometry, that's going to be 180 degrees. So linear geometries will always have 180-degree angles. Trigonal planar, which is a little more rare, it has to do with the boron atom like we discussed earlier in class the other day, okay, with 3 satellite atoms, all right. If you push them all around as far as you can, you will wind up with a 120-degree angle between the different electron pairs, whether they're bonded or non-bonded. Now, if you look here with this notation, A with two satellite atoms, but then 1 electron pair. So what that means, let me get my, okay, here you actually have an atom on the end of these two, okay, so it might look like that, okay, but then right here you don't have an actual atom, you have your non-bonded pair. They count as one of those legs, okay, so 1, 2, 3 domains. There's still 3 domains. It's just that one of these electron pairs, this one up at the top, does not have an atom attached to it, okay, but it's still counted as a domain. So you can see what happens when you get to tetrahedral. You can have a tetrahedral shape with 4 atoms, 4 satellite atoms, or you can have 3 satellite atoms with 1 electron domain, or 2 satellite atoms with 2 electron non-bonding electrons as a domain, okay? We're going to show you this winds up as being a bent shape, okay? Trigonal bipyramidal, just to talk about the shape, it's got 5 electron domains, okay? These 3 in the middle, so this one, and this one, all right? Those will be similar to the trigonal planar. They will have 120-degree angles between each other. But then if you take these other 2, I'm using yellow, that doesn't help, okay? They're 180 degrees from each other, the yellow ones are, but they're only 90 degrees from the red angles, the red electron domains that I've got there. So you've got 2 angle differences here. You got a 120-degree angle between the red ones and 90-degree angle between the yellow and the red domains there. Okay, octahedral, okay, is the same thing, but you've got 4, 1, 2, 3, 4 going around the center. Those are 90-degree angles, but then because of that, you also have these two, which are also 90-degree angles. So the angle in octahedral will always be 90 degrees. The only one with 2 different angles is trigonal bipyramidal. Okay, so here's a better look at that. All right, you can see the angles. You can see down here at the trigonal bipyramidal, you can see where the 120 angles are compared to the 190s. Okay, so now here's how to determine it. All right, we simply just count the number of electron domains, and that'll tell us the electron domain geometry. All right, so let's see what I got going here. So how many electron domains? 1, 2, 3, 4. What has 4 electron domains? Hopefully you guessed tetrahedral. This will be a tetrahedral electron domain geometry. Now I want to point out, let's see if I can get it here. This right here, electron domain geometry. All right, that's not what you visibly see. So these right here you don't visibly see. Okay, they're electrons, but you don't see that. If you had a magnifying glass strong enough to see this, you would only see these 3. So even though this is a tetrahedral shape, what we visibly see is going to be what we call trigonal pyramidal, and we'll talk about that next. That'll be the actual molecular geometry. All right, here it's going to go ahead and go through what I already went through. There's your 4 domains. 4 domains means that it is well, there's your choices. The one with 4 domains is going to be the tetrahedral. And there's the answer. And that is your electron domain geometry. Again, not your molecular, which leads us to molecular geometry. This is what I'm trying to say. This is what it actually looks like. So you'll have an electron domain geometry that might be different than what you visibly see. Sometimes they're the same. Okay, sometimes they're different. This will show you. So here they're going to use a tetrahedral. Right here where I'm underlining, they're talking about that is your electron domain. So it's going to have, these are the possibilities when you have 4 electron domains. Okay, you can have this instant here where you have 1, 2, 3, 4 satellite atoms. Okay, so your electron domain is clearly tetrahedral. Well, your molecular geometry, what you visibly see, would also be tetrahedral. Then you might have this, where your 4th electron domain is like these non-bonding electron pairs, okay? You will visibly not see this. It would be like, let me get the highlighter. It would be like we scratch that out. You can't see, it's there, but you can't visibly see it. What you visibly see will be over here, okay? And that clearly does not look like a tetrahedral. That is what we call, well, it doesn't say, oh, it says it right here, tetrahedral bipyramidal. That's what we've got over here. Okay? I'm sorry, trigonal pyramidal. I'm going to give you a cheat sheet in class that has all these shapes on it. All right? And then the other circumstance is water. Water actually has the electron domain. It has 4 electron domains like this, 1, 2, and it's got two non-bonding pairs, okay, these E2s. Well, with water, they're there, but you don't see them, okay? They're right here and right here. You don't see those, though. All you see is the bent-shaped atom that we know of when we're talking about water. And that's how it gets to be bent-shaped, because you've got the repulsion pushing these other away from center. All right, so this is just a statement of what we've been saying. The electron domain geometry may not be the actual molecular shape of the molecule. Molecular geometry is the actual shape. These are two different things. All right, they can be the same, but they don't have to be the same. All right, so there's a difference. Your electron domain geometry over here is tetrahedral. But the same atom, if you're looking at the molecular geometry, you don't look at these unpaired electrons, so your actual shape is trigonal pyramidal. By the way, this is the ammonia atom, or molecule. Can't get my words straight. All right, so a few things we've got left to talk about here is the effect of, first, the effect of non-bonding pairs on the repulsion. All right, the repulsions of non-bonding pairs are stronger than the repulsions of bonding pairs. Okay, so when you've got these two, bonding pairs over here, non-bonding electron, this non-bonding pair of electrons, they will have a stronger push. Okay, like this. They will push stronger than the ones that's bonded to an actual atom. All right, so they actually push with more force. All right, so here it is. You can see what happens. If this pushes with more force, it pushes these actual bonded pairs down farther away from the top. All right, if they're pushing away from the top, they're pushing closer to each other. So the angle down here in the actual molecular geometry, the actual angles between the actual atoms, okay, is going to be less than the 109.5 that we talked about in a normal tetrahedral. Okay, that's if there's one pair. What do you think is going to happen if there's two pairs of non-bonding electrons? Okay, like in water. All right, here we go. Now we've got a lot more force pushing these away from each other, or away from the center, but more towards each other, so these get closer, and so our angle gets even smaller, 104.5. I hope you can see with my drawing. My drawing is awful, but I'm going to learn and get better. All right, so there's the examples of what molecules they could be. Okay, and the same thing holds true when we're talking about double bonds. All right, the double bonds actually, think about it, more electrons in a double bond. Right here you've got how many electrons right here? That's 4 electrons. So 4 electrons are going to have a stronger push than 2, so it's going to push on the other bonded pairs a little tougher. So whereas this would be normally would be a 120 degree angle. I almost got it there. 120 degree angle because it would be trigonal planar. Because of that extra push, because of the double bond, it makes the bond between oxygen and chlorine bigger, 124.3, and the bond between the angle between the chlorines, 111.4, smaller than 120. So it's the same effect as the non-bonded pair. It has a greater repulsion. So it also affects. All right, last part we're going to talk about is large molecules. You can break them up into several geometries based on central atoms. Can anybody look at this and guess there's 3 central atoms? What are the 3 central atoms? Hopefully you can look at the sketch and figure that out. The first central atom is going to be the carbon on the left. All right, so we're replacing that here. So we'll just talk about the geometry of that. What's the number of electron domains? This will be a good example of the difference between electron domains and geometry. Hopefully you guessed 4. 1, 2, 3, 4. Okay, that's your number of electron domains. So that's also going to give you your the electron domain geometry is tetrahedral because we've got 4, and our predicted angle would be 109.5. Okay, because that'll be a tetrahedral shape. What's the next central atom? Hopefully you figured out it's the second carbon. Okay, and what is our number of electron domains causing our electron domain geometry there? Well, you've got this one counts as 1, and this one. So that's a total of 3. If we have a electron domain geometry with 3 electron domains, what is the shape? Trigonal planar. And if it's trigonal planar, the angle is going to be 120 degrees. The last central atom is that oxygen. Okay, how many electron domains here? 1, 2. Now we're talking about electron domain geometry, so we also have 3 and 4. So our electron domain geometry is tetrahedral with 4. Let me ask this just real quick. What's going to be the shape of this part? The molecular geometry, not the electron domain. What shape is this going to be? Hopefully you said bent, like water. Okay, because it's got the 2 non-bonded pairs. Okay. So remember our Lewis diagram up here. This is our 2-dimensional way of drawing it, but the molecule's 3-dimensional. So here's what it looks like down here towards the bottom. All right. Notice it's 3-dimensional. You've got at the oxygen right here, you have the bent shape like I was talking about. The central carbon, trigonal planar in both electron domain and molecular geometry. And up here with the first carbon, you have the tetrahedral shape, and that's for both the electron domain geometry, and the molecular geometry. Okay. There you go. This is information for that you don't need when you take organic, and I believe this is the end of the slideshow. So hope you guys. This wasn't torture. I hope you could follow, and I'll get better at doing this. And I'll sign off by saying, okay, all right, and let me talk now. Go answer your questions on the discussions. See you guys tomorrow.